I'll wait for a couple of more minutes for more people to join, and then we can start. So let me give you a brief overview of we are going to cover today. So today we are going to discuss mainly about different types of optical telescopes and how you can use these telescopes to do astrophotography, do some scientific observations. And to begin with, we are going to show you the different types of telescope setups, the different types of attachments that exist in order to connect your cameras, cell phones to the telescopes, and how you can utilize the devices that you already have to their best potentials in order to take observations using basic telescopes that are available in the market. We are also going to tell you about how you can make your own telescope. So you have the flexibility of building your own telescope with whatever focal length you have in mind, and you can choose the aperture of the telescope that you want to build. And we will also demonstrate a couple of models of telescopes that we have put together in IUCAA. So IUCAA has been involved in telescope making uh, for almost 25 years now. And this has been a long tradition of IUCAA to encourage students to build their own telescopes and eventually use those telescopes to do some simple yet effective astronomical observations. So we will talk about things like capturing your own photograph of the moons, capturing photographs of the sunspots safely, and also how you can do photometry of stars. And you must have heard these different methods like photometry, spectroscopy, spectrography, and all these things during the course of lectures of the summer school as well as RCAA. Now, how to do this at the amateur level is another story. So let's begin with looking at different types of telescope setups. Before going to that, let me quickly show you a couple of slides. So is the presentation visible to you guys? So any one of you can write in the chat. So I think that so we have divided the telescope making session into three parts. The first one is the telescope making primer, right? And there are also going to be some documentation that we will share for choosing your telescopes. So it has also been divided into two parts. The first is a basic or beginner level where you can choose your telescope for visual observations. And how do you exactly, what all do you consider while choosing your telescope, while choosing your equipment, and what different purposes can you use your telescopes for? So the basic important feature that you can use it for is fun observations and spotting. So before actually starting the presentation, let me begin the recording first. Just a moment. So we will be joined by Mr. Samir of IUCAA shortly. So he will begin with the presentation with a small set of slides. He will talk about the basics of optics, different experiments that you can do. And as soon as he covers his topic, I will show you the telescope demonstrations in the later part of this session. So I would like to invite Samir to please take over. So let me just make him. Samir, you can share the screen now.
All right. Thank you. Thank you so much, Atharva, for holding the fort while I was away. So, and this is really nice again to meet so many of you. online and on this particular topic, which is a favorite of us astronomers, which is basically about telescopes. Now, we're talking about optical telescopes today. And so if you've noticed that the topic for today is optical telescopes primer. Of course, there are also other kinds of telescopes which you would think that may not be accessible to us, like radio telescopes, which need to be very large for their basic physics, basically, because of their basic physics. But then there are also ways of making those. I'm sure they will be referred to at some point of time during this session. But optical telescopes are the most accessible and easy to use for us here. And this is basically something which we do every day. Look at the optical light, visible light, as it is commonly called. So this light is something we can see all the time with our own eyes, which may not be telescopes, but they are sensitive instruments to sense this light and give us a lot of information. Now, telescopes are just another additional aid to our eyes, which make us look into the universe in a more better way. So, therefore, to go into optical telescope basics, I have today a sequence. So it's like you think of doing something, and then one thing leads to another. So if you're thinking of a telescope, which we will describe to you, telescopes and their accessories, but the discussion will not finish there. So we have telescopes and accessories, and I'm sure you are also looking forward to at some point of time having your own telescope. We'll be describing you how you can have your own telescope, what kind you should have, what sort you should have. I think Atharva referred to the video series where all this has been very well covered. Now, but that's one part of it. And so after you have the telescopes, you will also have to have a mount and its accessories on which you base the telescope. So it cannot just be the telescope. What you refer to as a telescope is usually the telescope and the mount. Okay, so we call what is really called the telescope is usually called the optical tube by in technical words, and then there's the stand, which is called stand in common language, but mount in technical language. We also will have imaging devices. So it's imperative that if you are using a very big telescope these days, you record what it is looking at rather than just use your eyes to see it. Of course, for amateur level telescopes, hobby telescopes, you definitely want to enjoy the sky views with your own eyes, and you will be able to see things easily with the telescope. The thing is to take it further. If you want to do more studies with what you're looking at, you want to even do something like beautiful photography, you need to have imaging devices. So we'll come to that. And then, of course, with all these things, you'll need the information about the sky. Where should we look at? What should we look at? How long should we look at it? What should we be observing in what we are looking at? What are the notes we should be taking? What kind of signs can come out? So all this is part of information, which is also a part of having a telescope and using a telescope. So let's see how far we can get and what we can cover in this. And then, of course, with all these things, this will lead to real observations with your telescopes. Okay, so hopefully we'll be able to give you concise and precise information about telescopes and all these things which lead to an observation from your side. Okay, so let's go ahead and start with telescopes. This may be a repeat for you, but telescopes are of different types. We have things which we call Galilean telescopes, just obviously because Galileo was the first person to use this kind of telescope to do astronomy. So for astronomical purposes, this was the first kind of type of telescope to be used, and it uses lenses to focus light, and that is the primary optical part of this kind of a telescope. So therefore lenses are made of glass, they refract light, So they are also known as refractor telescopes, refracting or refractor telescopes. Uh, in fact, I often ask people, have you seen a telescope in your life? And many of the commonly coming answers are, no, we've never seen a telescope. Then I ask them, have you seen binoculars? And most people have used binoculars to see far off objects, birds or mountains or sometimes stars. Not always, but birds and mountains and far off buildings, etc. They've definitely seen with binoculars. So if you look at it, binoculars are actually basically two telescopes, each for one eye, right? So it's kind of a misconception that a telescope has to be like this and you have to hold it like a pirate and look far off, and it has to be a Galilean. So let's see how this concept changes now. Binoculars are actually two telescopes. You can just close one eye and you'll have a telescope. So that's one kind of telescope, the refracting telescope. But about 100 years later, another kind of telescope came into use and has become very popular now, and that is the Newtonian kind. Now, the change which Newton and others brought into the telescope as an instrument was that the primary, which was the lens in Galileo's telescope, was replaced by a concave mirror. So you can see this says here primary mirror. I hope you can see the slide clearly. So this curved surface here is a concave mirror, which is polished and made reflecting on the inside surface. Okay, so that's the concave part. And in the Galilean type, as you can see, these are the parallel rays coming from far off, from objects which are almost at infinity, like stars and planets, can be, for our convenience, considered to be at infinity, giving parallel rays to us. And that is kind of focused by this lens to a point which is called the focus. Now, a concave mirror also can do the same thing. Only the issue is that when the light is coming from this direction, the mirror focuses it in the same direction, the opposite direction of the light. But then it's within the area where the light is coming from. In this case, it is going in the same direction of the lights, but so it's not if you want to see the light being focused, you will not have to go here and obstruct the light in the process. So you can easily put your eye here with an eyepiece and you can get the focused light. In this case, the light goes in this direction, and therefore there had to be an ingenious trick which was done, and that involved having a small flat mirror, which basically changes the direction of the light being focused from this direction to this direction. So it's from simple laws of optics that incident angle, if you can make it 45 degree, then the reflected angle would be 45 degree as well. So we get a 90 degree change in direction. Then you know where the focus is, and then you can adjust your eyepiece so that you can see the focus light. So that's the change which was brought in, and this became a big change in the types of telescopes. And you will see now that most of the modern telescopes, including the small telescopes we'll be showing you today, and some of the largest telescopes in the world, they are all using reflecting mirrors and reflecting technology for their primary. Okay, so this was Newton's basic telescope, which had a concave mirror and a small flat mirror here, which does obstruct some light, but the main purpose is sought that you don't have to put your whole head here to see the light. So what it does is, it kind of, since the cone is reducing, it only has to be at a certain distance where the cone is just enough wide enough so that it doesn't obstruct the whole path of light, but a small part. Okay, and then it is pointed in this direction. So that was a very basic idea, and it changed the way astronomy was done, because now you could, with this technique, this trick, you could have bigger and bigger primaries. The lenses are difficult to make. Best lenses are very difficult to make, and in fact, I think the best big lens in the world is at the max about 1 meter big. Okay, 1 meter in diameter. So that's some of the biggest refracting telescopes in the world have a 1 meter kind of a lens, and it's they haven't gone beyond it because it's pretty cumbersome. It's you have to shape it properly. Of course, you have to get so much of the glass into a proper shape. You have to maintain it in the proper shape because glass being like a fluid, it flows over tens of years. It flows in a direction of gravity and it can change the shape of the lens. So you'll have to find ways of not doing that. Then it has to be perfect. It should not have impurities. It should not have bubbles and imperfections. So there's a big process to do it, and it costs a lot. However, in a concave mirror, all you need to do is shape a thin piece of glass, so material required is less, into a proper shape, which is a parabola, and there you have it. Just put some reflecting coating on it. So you need not be too much worried. For small telescopes, at least, you need not be too much worried about the type of glass, etc., whether it flows or not, because it is not going to be very heavy. So that was an advantage, and cost, of course, is one of the biggest concerns. So Newtonians became popular, but over time, people thought that, okay, I have to, when I want to see something in this direction, I have to actually put my eye perpendicular to it. Okay, that kind of, for many people, that was inconvenient. So there was another technology which came in, which is called the Schmidt Cassette, which is an improvement on the Newtonian telescope. So what was done was, in this figure you will see it. So the concave mirror, instead of being kept whole like in this place, it had a HOLE hole inside in the middle. Now in this, of course, two-dimensional image, you will think it's two separate pieces of mirror, but it's basically a round mirror with a small hole inside it at the center. Okay, this is just a cross section, so it looks like two mirrors separated out. So this is just a small gap in the mirror, a circular gap, and that gap actually doesn't make a difference, because you see, even in the Newtonian, the light coming to this part of the mirror is kind of getting obstructed by the small mirror anyway. So here, instead of a small flat mirror, we put another concave mirror, and then with appropriate focal length, and the light gets focused in the same direction, just like the Galilean telescope. Okay, so although there is an obstruction, small obstruction, we are still being able to look at the object in the same direction of the flow of light. Okay, so you can put your eye here, and then it becomes like the other telescopes. So this was important. This may not seem important for a small telescope like a 6-inch telescope, which we will be showing you, and you'll see that if there's a telescope of this kind of a size. Okay, when you see me, it's one of my favorite telescopes. This is actually a Schmidt Cassette, but I was just referring to small telescopes. So you should know what small means. Small means of, let's say, your own size at the max. So for those telescopes, maybe Newtonian is better, because you don't have to put the whole telescope towards the sky and then look through it. So it becomes cumbersome to do that, unless you have a really small telescope. So if it's your size, you don't want to put it on top of a table or a wall or something and then look through it. Then in that case, Schmidt Cassette may not be such a great idea, but Newtonian suits that. However, if your telescope is enormous in size, let's say like the IUCAA telescope, which I will be talking about, IUCAA research telescope at Galilean, or other telescopes in India, which are 2 meter size, 3 meter size in diameter of their primary. For those, in earlier times, when they had a Newtonian type of telescope, the light would be reflected in this direction, and the secondary would be somewhere here at the top of the telescope, which is usually 3 stories high, right? And the astronomer would have to go there and see, or put their cameras there, right? Which then becomes inconvenient if the telescope has a huge size, right? So in that case, then Schmidt Cassette becomes nice, because all this is at ground level. Just remember, with the telescopes, you will not be looking at horizontally towards the ground. You'll be mostly pointing up towards the sky. So although all these ray diagrams will show you a flat telescope, it's hardly ever used like this. It's mostly at such angles, right? And you have to consider the practicalities of having these angles observed. And so in that case, for bigger apertures, Schmidt Cassette types are a good option. There are further advances where you started taking care of other things. So the introduction of a smaller concave mirror in the Schmidt Cassette caused some changes. Sometimes some aberrations came in because of the use of two different concave mirrors, right? So then came another kind of Markutsov Cassette telescope, in which there are other types of uh, uh, techniques used which do fold the light. A technique that is called folding the light. So light goes like this, goes here, and then it goes here. So basically, you have reduced the focal length by 2 times at least. Okay, that's called folding. Right. Now this one also has a corrector plate and a flat secondary mirror. So there are advantages of that you can get, and the tube basically becomes smaller and more convenient to use and carry around. Or if you have a bigger size telescope, then it's less bulky and it can be easily moved around. So these are the kind of popular telescopes which you would be hearing about if you get into the world of telescopes. If you start observing optical objects in the sky, visible objects in the sky. So Galileans are best for easy observations. If you have somebody in that you know in school, etc., these are the best to prescribe. For somebody who's got a more interest in the hobby of astronomy, Newtonians are good to have. In fact, Newtonians are easy to make by yourself as well. So we'll be discussing that slightly later, how you can make your own Newtonian. Schmidt Cassette and Markutsovs are, of course, definitely more difficult to make, and they do cost a bit, but they are a good option for something like a laboratory or an observatory in a college or a university department. So where such telescopes could be very handy, and you could actually have a bigger aperture, as it is called. The primary size would be bigger, thus giving you better light collection, better resolution, and better magnification given your sensor size. So all these advantages are there, and then you can better use these telescopes for scientific studies as well. So that's for if you're going for scientific studies, I think the later two are the better ones to choose. So that's the type of telescopes, and I just said this without showing the writing here. So these are the things. So 6 inches are the ones we recommend for wide field observations, outreach, for if you want to do sky observations with a lot of people together, if you just want to show the moon to your family, something like that. 6 inches are a nice option in reflectors. 8 to 10 inches are, as I said, they give you an improvement in light collection, etc., and they are easy to carry. 12 to 14 inches are something we can still consider research class, but they are costly. Easily affordable, although for departments of universities and colleges. So we go ahead. If you have a telescope, as I said in these images you just saw, all those telescopes had the primary mirror, which is has to be the best that you can get. It also has a tube in which they fit. But other than that, where the light is focused, you have to put an eyepiece. So if you're viewing through your eyes. So if you're buying a telescope, make sure you also invest in a good eyepiece set. Okay. So there are different kinds of eyepieces available. It could be like very low cost plastic ones, or high cost plastic ones with better plastic and better eye relief, as it is called. So the size of the aperture of the eyepiece is also important, because finally you are going to put your eye in it, right? Eye near it. So if the eyepiece allows you to see the light more easily, then you should go for that eyepiece. So we'll be showing you some eyepieces now. So here are some examples of eyepieces. So you can see there are various kinds, and these are colossal eyepieces, in fact, they're called, and they have a part which is made out of metal. So it's not just plastic. There are some plastic parts, of course. There are some rubber parts, glass parts, but a lot of it is lightweight metal, maybe aluminum sometimes. So you can see that there are various kinds. So here the aperture is very tiny. Okay? You can see here the aperture is very, very tiny. And here are the ones which have a huge, place where you can get a piece of glass where you can put your eye. So there are differences. I mean, of course, all these, of course, also differ in their focal lengths. Okay, and the focal length of your eyepiece defines how much magnification you will get. So it's basically the ratio of the focal length of the primary element with the focal length of the eyepiece that you are using. Right. So a 10 mm eyepiece will give you a bigger ratio compared to, so it's primary focal length divided by eyepiece focal length. So if you're using smaller focal lengths, you'll get a bigger magnification. If you're going for higher focal lengths of eyepieces, let's say 25 mm, 50 mm, then you'll get a lower magnification, but your field of view will increase. Okay, so you will be able to see more area of the sky, but the magnification, obviously, given that this field remains the same, the magnification will be smaller. So sometimes it's referred to as zoom, but I don't think that that's a good word to use here. So it's the magnification which the eyepiece causes, which is also important. But then when you're observing through it, it should also be convenient for your eye to see through it. So then you should go for some of the better eyepieces which have a bigger, what is called eye relief. Okay, and so there are options to choose from. We recommend having a good eyepiece set, preferably of this metallic kind. Okay. Then other than that, so this is what I wanted to tell you about, that if you are using an eyepiece of bigger and bigger focal length, you see more and more of the sky. Okay, so here you can see with a 40 centimeter eyepiece, you can see probably this part of the moon with the same telescope. So we are using the same scope. Okay, and with bigger and bigger focal lengths, more of the area gets seen, but the magnification becomes lesser and lesser. Okay, so if you can change all these circles into the same size, that's the effect you will get. Here, of course, it's just an illustration, but if you can change all these circles into the same size, then you'll see this will be highly magnified and this will be smaller, but you'll see almost all of the half moon here. And other than that, you can have solar filters and moon filters. Okay. With the telescope available to you, you may not want to start directly with things you do not know about, right? But the sun and the moon are there in the sky. They are known to you. You can easily find them in the sky, so you can point your telescope more easily towards them, right? So, but then it's not recommended to look at the sun at all, even with naked eyes for a while. But with a telescope, definitely never point it at the sun without a filter on right at the beginning. Okay, so the filter has to be at the beginning, cutting out almost all light. 99.99% of the light has to be cut off before it reaches the primary. Okay, because the primary is going to point, and just imagine if there is something at that point, what will happen to that object. Okay, and this light also gets concentrated, and it has to go through the eyepiece. And as you can see, so much collected light is now getting compressed and is going through the eyepiece. So even the eyepiece may burn if it's a plastic eyepiece, get heated up or melt. So that's for the eyepiece. Now imagine if your eye was there. Don't imagine, in fact. And always put a solar filter on your telescope if you're planning a solar observation. Never go without that. So solar filters are there. Moon filter is more of a different purpose. Now the moon can be really bright at full moon, but when it's half or when it's crescent, it's not so bright. So the moon filters actually enhance the contrast rather than actually like help you in cutting light so much. Yeah. So you can have both of these actually as accessories to your telescope as well. And one suggestion that we give is that make your own telescope. That is possible, and we'll come to that very soon. Okay. Now, this was about the optics part of the telescope's optics and what will go on the optical tube. Okay. Now, this tube will then be put onto a mount. Okay. Again, going back to the picture with me, right? So this is the optical tube, the white part with the eyepiece holder and the viewfinder, etc. That's the tube. This orange part is what connects the optical tube with the mount, which is here. Okay. So there are various parts of it which we will describe to you very soon. Atharva will be showing you all this in details. So that's the mount part, and that's what keeps the telescope steady, okay, and allows you to kind of keep looking at the same thing without having to adjust the telescope every now and then, every second. So telescope mount could be of, again, various kinds. Could be a very simple tripod, like your camera tripod. The photography camera kind of tripods can also be kind of a mount for your telescope if it's lightweight, if it's small. But as you go bigger and bigger, you'll make mounts which are called altitude azimuth mounts, alt-az mounts. Okay, and they may not remain the same kind of tripod which you use for a DSLR camera, but they might become bigger and thicker and sturdier given the weight of your telescope. But what I'm mentioning here is the alt-az part. Of course, all telescope mounts have to be sturdy and strong to keep your telescope safely up there. But then they are also used to move your telescope in various directions. So the alt-az mount basically serves the purpose of moving the telescope in these two axes. So what is altitude? Altitude is up and down. So from if you want to go to some angle right from the horizon to the zenith, which is at 90 degrees from the horizon, this is the altitude. So it goes 90 degrees in range, okay, from horizon to zenith. So that's the altitude movement. And then while you are doing this, you may also want to move the telescope in the azimuth motion. And of course, yes, you guessed it right. It is the left-right movement. Okay. But of course, we don't say left-right in this case. We say that means x number of degrees, n number of degrees from the north, exact north. Okay. So if you know where the North Star is, in which direction, then from that direction, you count the degrees and you count, let's say east will be 90 degrees from north, and then south will be 180 degrees, west will be 270 degrees, and back to north would be 360 degrees or back to 0 degrees. So that's the way it is counted. It is counted clockwise, the azimuth axis. So alt-az, that's what the tripod with an x axis and y axis kind of movement allows you to have. But this may seem useful to you in the beginning because it's easy to use. It makes it easy to point to any object in the sky with just an x, a combination of an x and a y movement. But there's another factor, that we live on the Earth, which is round and it's got its own rotational motion around its axis, right? And because of that, the sky seems to move from the east to west. The sky objects move from the east to west in the sky. They move at different rates. In fact, because if you look towards the northern side of the sky, the things will be moving smaller because they have to make smaller circles in 24 hours. The things towards the equator of the sky, they move faster because they have to make a much bigger circle in the sky during 24 hours. Okay, so I'm just talking about the apparent motion of the sky. Now, if you are pointing to some object in the sky, and yeah, I think I'll just show you some of the examples, pictures. I forgot this. So this is one of the alt-az mounts that I was referring to. It is a tripod, a much sturdier tripod with a mount here. But it may have to be improved to a equatorial mount. So equatorial mount is basically something which still has two axes, okay, but one of them is aligned with the Earth's axis, okay, and so it's parallel to the Earth's axis, and therefore if there's an object which moves along a large circle, a big circle in the sky, which is something like a latitude of the Earth, but in the sky. Okay, so if some object is moving along that large circle, then this kind of mount will allow you to track it, to follow it. So you will only have to move one axis of this mount to keep following or correct for the motion of the object in the sky. Okay, so that becomes very handy when you are wanting to observe something for a longer amount of time, or you want to constantly keep looking at the same object over a certain amount of time, okay, certain period of time, without losing time and finding it again and again and again. So this kind of a mount becomes very handy in that case. Okay, so for hobby telescopes, an all-toss mount is perfectly fine. This is, I think, a 5-inch, 6-inch telescope with a tripod like this. Okay, and a mount which allows you to move up and down and X and Y. But if you're going for a better observation, if you're going for astrophotography, if you're going for scientific studies, equatorial mounts and its different kinds are a must to have. Now, in this equatorial mount, what is shown, you have these long handles that you can see, okay, on that side and this side. These are the fine-tuning handles, and you can slightly change the direction of the telescope in one axis only, okay, with each of these, depending on what you need. So, but then if you are doing it manually, then you'll have to keep doing it all the time. So you have to keep changing the direction slowly over time. Now, an ingenious method to overcome that factor of you having to constantly attend to your mount and changing the direction of it to catch an object all the time, you can add a tracker motor to it. Okay, so the tracker motor basically, instead of this handle, there's a small motor, electronic motor, which attaches here, and this motor has a rotation period, so it turns once in 24 hours. Okay, and that's what we were trying to do. So we were trying to counter the Earth's motion, which is once in 24 hours. So now this motion, this motor is basically helping us do the same, but counter that motion. So the Earth is turning in this direction, it moves in this direction, so it can follow the object in the sky all the time, right? So it's just a simple equatorial mount, but with a tracker motor attached. That you can have motors on both the axes, and then it becomes a motorized mount. You can even, if you are any engineering minds here, and you can even try to make a remote which attaches to these motors, and then you can give remote instructions to them to move around, right? So that's what is included in these few points. So if you have a tracker motor, you can create a remote for it, or you can make you can add a computer to the remote, which then calculates the position of some object, and when you press something, moves the motors enough to take you to that object. Okay, so that becomes a computer control mount. Maybe now we can even have an app control mount from your that could be used from your mobile phones. These are just I'm just throwing in some ideas which can be done. This is how the computer controlled mount would look like. And I don't want to make any advertisements, but this is one of the more popular mounts which is used by several colleges and universities. So you can see how how sturdy it is, and this can easily take up the weight of a 10-inch, 12-inch kind of a telescope tube. Okay, so these are the mounts and accessories that you need to have. You might be wondering what this piece of iron is. So this is just the something called the counterweight. Okay, it will be there in all kinds of equatorial mounts. So this is a weight which will balance the weight of the tube, which is not here. Okay, so I'm sure you're finding these pictures very odd because the telescope is missing. What we call the telescope is missing. Telescope usually goes onto the mount, and then because it's a big weight, you have to put a counterweight on this side so that the axis can be balanced, and if you're holding the telescope at horizontal, then it will not move by itself in another direction, thus causing problems for the motor. So those are the mounts and accessories that we can talk about. And as I said, this is one of the telescopes that we use here. It's a Schmidt Cassette telescope. It's a Cassette telescope, not a Schmidt Cassette, and it's a 5-inch aperture, and it's got a motorized mount, not an automated one, but a motorized mount. You can see this. This is the motor which comes in a box. You can buy it ready-made as well, and you just fit it here into the axis, and it can be switched on so that the sky tracking turns on. Of course, before doing all these things, you have to point this axis, which is going to be parallel to the Earth. So this axis has to be pointed exactly towards the North Star, or actually the North Pole of the sky. So North Star is not exactly at the North Pole of the sky. So depending on the accuracy of observations you want, accuracy of tracking you want, you will have to spend a lot of time aligning this telescope. So that's one telescope at IUCAA. We have several more, and then of course we have the biggest one, the IUCAA Galilean Observatory here inside a huge dome. This is a 4-story building, 4 or 5-story building with this telescope, a part of the telescope sticking out. The rest of the important part is inside the building. This is just the dome. It's not. It's more like a cylinder. Dome is just a term we use for the enclosure of large telescopes. So this is at a place which is 80 kilometers away from Pune. It's called Giravli, and there's a hill there whose height is above 1,000 meters of sea level, and it's a good place for having a telescope like this. So, in general, if you were here present at IUCAA attending this course in person, you would have been definitely taken to this telescope for a visit. So, of course, I'm just taking this chance to give you at least one glimpse at this lovely observatory which is there. Hope you can return sometime and have a look. Okay, quickly going into imaging devices, which will be covered later, but these are the ones which are available. They, of course, range from the simple mobile camera, which you are carrying around in your pockets these days, to the what are called the prosumer, the in-betweens between consumer cameras and professional cameras. So these have, great zoom, great possibility of changing your aperture and your shutter speed, etc. But the lens cannot be removed. So the lens remains there, and you have to just use that lens. But still, it is possible to use these also for imaging through your telescope. But the best ones to have, if you are going for a low-cost setup, a medium-cost setup, let's say, are the digital single lens reflex cameras, the DSLRs. Digital is the new addition, in which there are very good digital sensors inside the camera, which are single lens reflex cameras, in which the lens can be removed, right? So you have a very nice sensor without a lens, and now instead of the lens, you attach the telescope to the camera. Okay? And there are attachments available. So I have pictures. Sorry, I should keep missing this. So this is the DSLR I'm talking about. So the prosumer cameras kind of are like this, which has a body, lovely body, lots of features, etc. But their lens cannot be removed. It's a fixed lens. It's got a fixed range of zooms. It can cause a lot of aberrations also, because it's lenses, a huge set of lenses. But here in this DSLR, you can see the lens is gone, and right behind here is the shutter mirror, but behind it is the digital sensor. So it's a bare digital sensor ready to take in any light which comes to it, and this part actually can be attached to a telescope. Okay, so instead of the eye or looking at, even the eye has a lens which you have to pass your light through, reach your sensor, your retina. This camera also has a lens. Here there will be no lens in between. It's just the telescope's focus light, reversing and then going into the sensor. Okay, and it's one of the better options if you do not have access to what are called the CCDs, or the charge coupled devices, which can be really, really sensitive and really, really costly also. Then if you don't have access to that, then DSLRs are one of the best choices to have in amongst imaging devices. Okay, so of course, then if you have a department, if you want to do better studies of, let's say, photometry type, or if you have like a grating with which you might want to do some spectroscopy and record the data without much errors, without much noise of the sensor, then CCDs and some similar cameras are really good, and although a little costly, they can give you really good data right with your small telescope also. So these are imaging devices we would be covering them in our upcoming this and the upcoming talk. We will also try to show you an observation taken with one of the telescopes sitting on a mount and using an imaging device. But of course, as I was saying, that you need to know about the skies. So if you are not assuming that everybody has a good experience with the sky and a good knowledge of the sky and real practical knowledge or observational knowledge of the sky, then you can start with gaining information about known objects like the International Space Station, satellites, and there are apps like the ISS detector, Heavens Above, okay, the websites and apps which can give you information about these things. But then after you have kind of known about these known objects, but you've actually seen them yourself, you can then go on to sky maps. So sky maps give you a proper map of the objects in the sky. So these could be stars, these could be other objects including nebulae, star clusters, even galaxies. Okay, so these are out there, but of course you cannot see them with your naked eyes. However, if you know that, okay, I know that this very faint object is besides a brighter object. Okay, then you can point to the bright object and then slowly move your telescope around by that many degrees to reach that faint object. So for locating these bright objects, at least you can use apps, websites, and softwares like Google Sky, Stellarium, Carte du Ciel, Celestia, etc. So Celestia is not so much, but at least these first three definitely give you a map of the sky. Okay, so feel free to use these. These are all open source, and they can go right away onto your desktop or onto your phone also these days. So with these, you can plan your observations there. And once you get familiar with the sky by looking at it over and over and over, and also seeing the changes of it over a season maybe, then you can start planning your observations. These are a few suggestions that we have that you could study. So you would study the moon. You could, it's easiest to catch, doesn't move out too fast out of your telescope field. Even if you don't have a tracker motor, you can easily do a good observation of the moon, because it's quite big in the sky. In general, for a common person, if you say it's only half a degree in the sky, it sounds very underwhelming. But half a degree for a telescope of 6-inch size is a big lot. And you can see a whole lot of features which you will not be able to see with your naked eye on the moon. And then there are other, so these would be observations of beauty to begin with, but then these could easily become observations which are used for various kinds of studies, including finding like the depths of craters on the moon, the heights of some of the hills or mountains on the moon, right? So these are things you could yourself start doing, other than identifying places on the moon or patches of land where some lander has been put there, or like Chandrayaan, it's landed there in some way. So these are fun things to do. But then, as I said, that you can also have better observations of the moon with a 6-inch kind of a telescope. Then solar observations are there, and I think we'll be trying to show you both of these, lunar and solar observations, on the next planned edition of this optical telescope primer. So solar observations range from looking at the sunspots, looking at the changes over the sunspot cycles. You could even have telescopes which have H-alpha filters, so you can see the sun in a different wavelength of light. Right? There are even scientific experiments to be done, like the limb darkening experiment, in which you try to figure out how much of that atmospheric extinction is there at the edge of the sun compared to the center of the sun when you are looking at the disk face on. That's few examples of what you can do with solar observations. Then there are planetary observations, which of course relate to the other bright objects other than the sun and the moon. Venus, Jupiter are very bright objects right now in the early morning sky. So do wake up and have a look. Even Saturn is there and Mars is there and Neptune is there, but they may be slightly more difficult to identify. Okay, but with a small telescope, you can easily point to them. You can see phases of Venus. You can see the Galilean moons of Jupiter. You can see the rings of Saturn, and just have a either a very good time looking at them, or you can study them, right? So what I was mentioning is something like you could see phases of Venus, and you can photograph them over a certain period of time. With the same magnification, you can see in this lovely picture that Venus has increased in apparent size to us. So it was this big when it was in a gibbous phase. Yes, Venus has its own phases, and over time, with the same magnification, it has grown so big, but it has become crescent. So it's basically one of the reasons how Galileo discovered that Venus has phases, and then he could think of a heliocentric model rather than geocentric model. With Jovian moons, the Jupiter's moons, you could see Jupiter and 4 of its moons, the small telescope. And there are various things which happen there. So the moons, they go around Jupiter. There are transits, which mean they go behind the Jupiter. Okay, there are eclipses in which you can see the shadow of the moon on Jupiter. So basically, if you were on Jupiter, you would be seeing a solar eclipse happening. You can find out their orbital periods. You can see if the orbital periods are remaining same or changing for a period of time. You can even track Jupiter's own rotation. And then there's this challenge of finding the speed of light using these eclipses and transits of the moons of Jupiter. Okay, and this was used by Reamer at not now, but much earlier, and he actually could find the speed of light by observing the motions of and the timings of transits and eclipse of Jupiter's moons when Jupiter was closer to Earth and when it was farther away from Earth. This is a graph. You can see if you have good observations and times, etc. Then this graph can tell you about the orbital periods and changes, etc. of the Jupiter's moon. So it's not just looking at it, but you can have a lot other studies from your small telescope as well. Occultations are actually something similar to what I said just now, the transit. So if there's an object in front of you, closer to you, and the star is, of course, much farther behind this object, which is either visible or invisible. So it could be the moon or an asteroid, which is not so visible. So if it covers the star behind it, then it's called an occultation. It can give a lot of information about the object which is going behind, and also about the object which is in front. Then, as I said, the stars themselves, right? The stars themselves can be studied, and many stars have various kinds of colors, spectra. Then there's also the variability factor, which is there. Many stars actually vary in brightness. Their brightness changes either minutely or very significantly, and there are reasons for different reasons for these changes. So they can be studied. Their life cycle can be inferred. For example, maybe knowing the Husband-Russell diagram, HR diagram is one of the examples of where stars were classified according to the stellar spectra and their luminosity, and they basically gave you this plot which tells you that if you know where the star is on this plot, you can know its mass and from its spectral class, you can get to know many of its properties. Okay, so and then you know that there are groupings of these kinds of stars, like white dwarfs are here, giants are at this side, and this main sequence stars are like the sun, which are here. So you can make your own HR diagram with a smaller set of stars. This might be many stars there. Then, well, of course, if all this is great for you, you can also do a lovely astrophotography. There are many objects in the sky. You can, of course, take wide-angle earthly views with your DSLR, even without the telescope. but you can look at planets, you can look at deep sky objects. So this is a nice sequence of planets some amateur astronomer actually did with all the planets imaged at the same magnification, right? And you can see it's a lovely collection of pictures. You can go for deep sky objects like the Orion Nebula, which is always breathtaking. Okay, and the Eagle Nebula. There are many such objects. There are galaxies which you can photograph. This is M81 and M82. You know the importance of M82 now. Uh, First black hole to be observed. Uh, Imaged rather. So that's something which you can also catch in your camera. Of course, you can't catch the black hole, which is a very, very, very tiny part of this huge galaxy. Yeah. Right. So and then there are other ideas which you can come up with. And other than that, there are some project ideas also. If you're part of some department of physics or any other such stream where you want to do some projects with astronomy, you want to have some small observations which could lead to a small short study, you are welcome to get in touch with us, and I'm sure our team will be able to suggest some ideas to you. So with that, I will stop this now, and thank you all for being patient. Now, Atharva, I'm sure, is standing by and quite eager to show you the assembling a telescope together to make one. So thank you very much, Atharva. Please take over.
Thank you.
Share screen.
So before we show you the actual telescope setups, let me quickly recap what Samir just showed. So these are the different types of mounts that we are going to see right now. And what we are going to demonstrate is there are many different types of cameras that you can use for astrophotography. And not just astrophotography, you can also use the different setups for scientific observations as well. So I hope that you can see the Google Chrome screen. What I want to show you is the different types of mounts that are there. The first one is the Equatorial Mount. The second one is the Alt-Azimuth mount. So both of these mounts have been attached to a pyre, right? So this is used when you have to attach a telescope permanently or for a very long time at a certain location. But usually in the commercial market, when you purchase a telescope, it is accompanied by a tripod so that you can fold it and carry it anywhere, and then you can set it up according to your need at any location. So instead of this pyre, you will see a tripod in a commercial telescope setup. The rest of the mountings will be different. The first one is called the equatorial or German equatorial mount. The second one is Alt-Azimuth mount, which has the horizontal motion and north, south, east, west motion, and the vertical motion, up and down. So using the combination of these two motions, you can point to a certain object, and then using different set of eyepieces, you can zoom in depending upon what object you are observing. So if you are looking at a planet, you would like to see a lot closer details of the planet. So it's a good idea to use a higher magnification eyepiece. So we'll also discuss about how to calculate the magnification, how to calculate the field of view. Then moving further, before we do that, let's understand these terminologies, because when I'm going to show you the telescope, I'm going to use a lot of terminologies like OTA, focal length, focal ratio, and so on. So a focal ratio of a telescope is basically the focal length of the telescope divided by the aperture of the telescope. So it is a ratio. So it does not have any unit. So the focal ratio is often used to get an idea of the magnification or the overall effective aperture of a telescope. Now, if you know the focal length of the telescope and if you divide it by your aperture, then you get what is known as a f-stop, or the focal ratio of your telescope. Now, in case of a telescope which has a focal length of 900 mm and an aperture of 102, which is almost 4-inch telescope, you can see that the focal ratio is f8. So you must have seen this number. So those of you who have used a DSLR camera, you must have seen this aperture value or f-stop value. So that is nothing but the effective focal length divided by the aperture that you are using. Now, you can also calculate the magnification of your telescope. So you know that the focal length of the telescope does not change. So once you get a telescope, it has a certain focal length which you get from the manufacturer. If you have made the telescope by yourself, it is in your hands what should be the focal length of your telescope. Then using different combinations of eyepieces, you can achieve different magnifications. So in case of the example shown on the screen, for a given telescope of focal length 900 mm, if a 25 mm eyepiece is used, you just divide the focal length of the eyepiece from the focal length of telescope, and that will give you the magnification. So it is 36x magnification, meaning the magnification achieved using this setup, a 25 millimeter eyepiece along with a 900 mm focal length will yield 36x magnification as compared to the view seen from the naked eyes. So this is how you calculate the magnification of a telescope, and this is how you calculate the focal ratio of your telescope. Now, field of view is another important factor that Samir already covered. I'm just revisiting it because I'm going to use these terminologies, so I don't want you to get confused. So the field of view of the eyepiece is often given by the manufacturer. So when you buy an eyepiece, the manufacturer will tell you the apparent field of view of the eyepiece. It can be 40 degrees, 80 degrees, 60 degrees, depending upon the type of the eyepiece you choose. So if you don't understand the different types of eyepieces just yet, don't worry. We will discuss more in the next session. So field of view is simply the amount of area of the sky that your eyepiece can show you. So the larger the focal length of the eyepiece, larger the field of view. Smaller the focal length of eyepiece, smaller the field of view. But again, smaller the field of view, more is the magnification, and larger the field of view, less is the magnification. So to get a very quick idea, let me just show you a graphic. So just a second. So you can quickly see this graphic over here. So here the magnification keeps on increasing from right to left, but the field of view keeps on decreasing. So this is a very good visualization where you can get a rough idea of how the field of view gets narrower and narrower as you go on magnifying. So this is very intuitive. It makes quite good amount of sense. Now, for attaching your cameras and other equipments to the telescopes, there are many different ways. So I will quickly steer through the different instruments that we use in astronomy. So this is a DSLR camera that most of you have seen. You also have used web cameras as well as you all do use mobile phone cameras. We can also attach a CCTV camera and a point and shoot camera to a telescope. You can make use of specialized planetary cameras or CCD cameras. And then there are some advanced instruments like photometers and spectrographs. So, of course, we are not going to talk in detail about these advanced instruments right away, but we are going to talk about the instruments that you already have in your homes, which are the DSLR cameras and your cell phone cameras. So, a cell phone can be attached to the telescope using a mobile phone adapter, and a DSLR can be attached to the telescope by two methods. The first method is called a piggyback mounting, where a camera is attached on top of the telescope body using a bolt. So camera body often comes with a groove at the bottom where you can screw in, or which allows you to attach the camera to a tripod. So instead of attaching the camera to the tripod, simply imagine attaching it to a top of the telescope. So this mounting style is known as a piggyback mounting. It's just the name. Then on the center, you can see that there is a mobile phone adapter. So you can make your own mobile phone adapter using some or the other kind of instruments lying around at your house, or you can simply buy a mobile phone adapter on many of the sites which are there. Amazon is there, and so many more 3D printing sites also have these models. So if you have access to a 3D printer, you can simply print one. Then there is a third image which shows you the T adapter mounting. So I'm going to show it to you right now. And after seeing the two types of mountings, then we are going to conclude this session. So the T adapter mounting is simply you remove the lens of the DSLR camera, and in place of the lens, you attach a T-ring adapter. And that T adapter then allows you to insert the camera in place of the eyepiece. So your camera as a whole will act like an eyepiece, and you will be able to image whatever is seen through the telescope. So we will also try to see that. And then at the bottom, there is this variable eyepiece projection assembly. So some objects or some astronomical objects are too small in angular size. Perhaps planets like Saturn or Jupiter have some beautiful features. So using an eyepiece in combination with a camera gives you a a larger magnification. So you can see a very small region on the surface of the Jupiter, maybe a great red spot on the Jupiter surface, or if you want to capture the rings of the Saturn in much more details, then using a eyepiece projection assembly in combination with your DSLR gives you some beautiful images, some beautiful results. So we are going to see these types of mountings, and in the next session we are going to learn, and we are actually going to demonstrate a live observation of moon as well as sunspots. So let's hope that we get some clear skies. Now what I'm going to do is I'm going to ask Mayuri and Tushar to switch on their cameras. I will stop my screen sharing. Now I will also put their videos on Spotlight. So Mayuri, are you ready now? Are you ready now? Okay. So you can start the video. I will remove my video from Spotlight. All right. So you need to switch your camera. All right. Perfect. So as you can see all three telescope setups. On the leftmost telescope, there is a mobile adapter that has been attached. So it is a simple ultra azimuth mount with a pyre stand, right? So there is a tripod at the bottom, tripod base at the bottom. Then there is a pyre stand, and on top of the pyre stand, we have attached a Newtonian telescope. So maybe if you could zoom in closer to the telescope's front end, you can see that there is a mirror at the bottom. You can just lift the telescope. You can lift the telescope up. Okay. So you can see a concave mirror at the end. So light coming from very far away, from maybe from stars and galaxies, will fall on the concave mirror. The light will be converged onto this secondary mirror on the front, and the secondary mirror is attached at a 45-degree angle. So no matter what, all light is falling onto the secondary mirror, it will be reflected at the same angle. So the light will be coming out at a right angle on the top of the tube, where we will be able to attach an eyepiece. But now in this case, instead of an eyepiece, along with an eyepiece, we also want to attach a mobile camera to it. So while we are looking at this telescope, Tushar Dada will now connect his cell phone, and we will try to see something through the telescope directly into the Zoom meeting. So this is something that we will do in the next session as well. So where we will show you the moon as well as sunspots using a mobile phone adapter and a DSLR camera setup. So while Tushar Dada is setting up the mobile, Mayuri, let's see the second telescope, which is a refractor telescope. Now this telescope is transparent. So ideally any telescope should not be transparent, because there is a leakage of light or the stray light which will fall onto the eyepiece. This telescope is made only for educational purposes, in order to demonstrate how light rays will travel inside the telescope. So if I were to shine a laser beam onto the lens, then the laser beam would appear to converge towards the eyepiece, and right before it focuses, the converged beam will be sent out of the eyepiece into our eyes. And that is how the light actually travels through the refractor telescope, and that's how the refractor telescopes focus and magnify the light coming from the faraway objects. So this is very much similar to the telescope that Galileo used, and he was amongst one of the first people to use telescope to look at the skies. And the discoveries that he made really changed the course of astronomy. It helped us understand and discover that there are moons to other planets, then there are eclipses of moons of other planets, and so many more things. So and eventually, after beginning from the telescope design of a refractor, we have now come across all the way up to the advanced telescope designs, like the Cassegrain telescope. So maybe let's see the third telescope now. So now this telescope is a go-to telescope. So it can be, it is a motorized telescope. So once you set an object, the telescope will then keep on tracking the object all the way until it sets. Now why this happens is, this telescope's axis, as you can see, is not horizontal. You can see its axis is tilted a little bit, right? So how much is it tilted? It is tilted equivalent to the latitude of wherever the telescope is. In this case, this telescope is right now in IUCAA in Pune. So the latitude of Pune city is 18.5 degrees. So that is why the inclination of the telescope's axis is 18.5 degrees. Why this has been done is we want to align the telescope parallel to the axis of the Earth. So imagine that the Earth is rotating around its axis, and this telescope, the telescope's axis is parallel to the Earth's axis. So if I rotate the telescope, then the direction of rotation of the telescope will be parallel to the direction of rotation of the Earth, right? So I hope you are able to imagine what I'm trying to say. We will definitely see the telescope in motion, and on the back you can see a DSLR camera. Now let me go outside, and I will talk to you from there. Just a second. So this is a DSLR camera. Okay. Okay. Now I think it will be audible. So what I just did was remove the lens, and now this is a T ring, right? So this T ring, just a second. To avoid echo, we have to mute the other computer. So now this steering also has these markings similar to the lens, right? So I will match the red dot with the red dot and simply attach it in place of the lens. Now, right now, because of this T adapter, which is which needs to be purchased apart from the T. So some telescopes have threadings which will allow you to attach the camera directly onto the telescope. But it is a good idea to take this T adapter. So I have now attached this. Now my DSLR camera is ready to be used as IPS. Now I will attach my DSLR camera on the telescope. Alright. So before I start this camera and show you the footage from it, let us quickly see what this telescope looks like. So now this telescope is a slight variation of a Cassegrain ray. So this telescope is called as a Ritchie-Chrétien telescope. What is different about this is it also uses a parabolic mirror which tries to converge the light, and the secondary mirror is a hyperbolic. Okay, and then that secondary mirror passes the light through the hole, uh, which is at the center of the primary mirror. The light enters the primary mirror, it enters the tube. You can see a lot of grooves over here, right? So these things are known as baffles. So these baffles are used to reduce the amount of stray light falling onto the. So something like this is also used in space. So if you want to send a space telescope, you often use baffles along with it in order to avoid any stray light or dust or any other debris to go directly towards them. Now this light is converged or focused onto the secondary mirror and sent back to the hole which is on the primary mirror. So then that light eventually falls onto the eyepiece. Now in this case, the eyepiece has been replaced by a DSLR camera. Now we can simply start the camera live view. Now the camera live view has started. Right now I'm just looking at some tree. So maybe I will move my telescope a little bit and have it pointed to some, I don't know, I think there is a building over. So remember that you should use your telescope for astronomical use only. I think we can focus something. Okay. I hope that you can see that the live view from the telescope is onto this camera screen. Right now, some trees are getting. But anyway, I think you get the idea. So, since this telescope is a little bit tedious to maneuver, what I will do is I will show you the live view from the zoom screen of the mobile. So you will get a much clearer view. But I think you get an idea that I'm not cheating here. I have really attached a DSLR camera and I'm showing you the live view. So since it is changing, you can get a good idea that this same exercise will be done in case of live views and photographs of the planets. So for planets, you can take videos and then stack individual frames of those videos to get some beautifully stacked images. Now let's switch over to Tushar view. So what he has done is, perhaps you can show him the setup. So on this telescope, there is this focuser. So this focuser has a rack and pinion, and this rack and pinion allows you to move the camera closer and farther from the telescope. What you are simply doing is you are focusing it, just like you might have used the microscope in your schools. So it also has this rack and pinion system where it moves the camera closer and farther from the telescope. Now, this mobile phone adapter has been slightly modified to be attached on the eyepiece. So this adapter gets locked onto the eyepiece. So I will quickly remove it and show it to you. This is self-made. So this is actually a little bit modified by Tushar Datta in order to change the eyepiece, and notice that the alignment is very much precise. So if eyepiece, so changing the eyepiece, what does it do? It simply changes the magnification. So if I use a 9 mm eyepiece instead of a 25 mm eyepiece, I'm going to increase my magnification. So it is that simple, and you can see the camera lens is exactly aligned at the center. So I don't have to move this mobile phone constantly and do the alignment. The alignment is automatically taken care by this fixture. So if whatever I just said is confusing, don't worry. You can buy a standard issue mobile phone adapter and you can simply use that. So this has just been done to avoid hassles for alignments. So, but this is going to make it a lot simpler to point the object. Now, Tushar is going to switch over the camera. I'll quickly go and spotlight this video.
So you can see the view from the telescope.
Just a second. Now I will spotlight Tushar view from the telescope. So you can see this is a slightly unfocused view. Now we are going to try and focus the image. We are looking out of the window, and we will probably see some trees or maybe a building. What we are looking at is the live view of a telescope, and I hope you are able to see some trees and leaves, right? So he's manually maneuvering the telescope, and the exposure is also a little bit overexposed right now. So the thing is that the telescope is indoors right now. So, but I think you get a good idea that what we are trying to do here. And imagine looking at the moon or maybe at the sun, and using your mobile phone camera, you can also simply zoom in digitally by just pinching your screen, and you can capture beautiful videos as well as photographs of all the objects. We can see some trees now, and they are getting focused. Oh, we can see a window now. We can see the window of a building which is very far away. Perhaps Mayuri, you can switch on your video and show them the building without the telescope. So you can see both of the videos side by side now. So you can see the building very far away, and we have pointed, or we have focused on a very small region of that building on one of the windows.
अरे ते काय आहे तो सापडतच नाही त्या पण मी मग
बट आता दिसत होती, क्लिअर दिसत होती. येस, आता हे झालंय फोकस. झूम करावं लागेल थोडं डिजिटली. But I'm sure that everybody now got a very good idea of what we're trying to do here. So let's quickly see the setups once again. Mayuri, if you can show us the telescope setups again. Wonderful. Now the roof solar panel is being focused, and now the antenna or the wind pane of the building has been focused. But very similarly, we can also focus the craters of the moon and also the sunspots on the surface of the Earth. Now it is very clearly focused. It's looking very clear. So with the normal phone, you can barely see the wind pane at all. But through the mobile phone, we have been able to focus it, and we can observe that how the wind is blowing. So it is a very simple setup, and it can allow you to take very effective observations of the moon, sun, as well as planets. So it is very simple to do this. Now, this is how the setup looks like. Now you can attach this to any telescope, and this can be used in combination with any phone that you have. So the initial alignment is important, that aligning your telescope, eyepieces center and your mobile's camera is a critical part. Once you have done that, then everything is ready. And also the DSLR camera setup that you can see in this image is also very, very simple. There is just a T-ring adapter that you need to attach instead of a lens, and it's going to be ready to use. So I would like to conclude this session here today because we don't want to extend it too much. The next session will be on June 6th. So we hope that we get some clear skies and we are able to show you a couple of observations actually taken through the telescopes. And we will also talk about some projects that you can do on your own. So it could be like observing lunar occultations. We will also tell you how to find them. And if you have any questions, this would be a very good time to ask them. So we can take some 3-4 questions for another 5 minutes, and then we can wrap up. So please feel free to unmute yourselves. So I have now allowed participants to unmute yourselves. Please raise your hands and ask questions one at a time. If you don't have any questions to ask right away, you can ask them on the Slack channel. Okay, Vinisha, you have a question. Please feel free to unmute.
So you said you will discuss how we can make our own telescopes.
Yes. So IUCAA has a beautiful telescope making setup, and we have a lot of resources on our YouTube channel for telescope making. So let me just quickly share the link on the Zoom chat. I will also make sure that I will share these links with you all on the Slack channel. So all the materials and all the important resources that were discussed today, we will collect them at once, and we will share it on the Slack channel by the end of the day. And we will also share it on the RCAA Slack channel with the help of Equatorial. So you can take a look at this YouTube channel. We also have a Telegram channel called IUCAA Telescope Making. So I would encourage you guys to join that channel. You will find the list of vendors who sell raw materials necessary to build your own telescope. We have this playlist which tells you the procedure and the entire method of building your own telescope. If you want to buy your own telescope, there are also videos which will help you choose the best possible setup for you. And somebody is asking about the cost of the telescope which is required. So all these questions have been addressed in the videos that I have shared. You can also ask these questions on the Telegram forum or the Telegram channel that we have called IUCAA Telescope Making. And it is a public channel. You can definitely join it. And we also have a Telegram channel called IUCAA SciPop, where we give out our regular updates of IUCAA programs and all the other activities and workshops that we arrange. So do you have any more questions about the today's session? Let's clarify them right away. If not, then we can conclude the session. So I don't see any hands raised. So thank you all for joining this session. On behalf of IUCAA SciPop, we would like to thank you once again for being patient, and sorry for extending the time. Let's meet on 6th of June for the next session. I'm sure there is another session tomorrow. So until then, see you all. Feel free to ask any questions on the Slack channel. And if you feel that we have missed anything, you would like us to include anything specific in the next session, please feel free to ask or mention that on the Slack channel. So the Telegram link will also be shared on the Slack channel. So you can just search IUCAA telescope making on Telegram and you will find the channel. So it is very simple. So thanks once again. So I'm going to stop the recording now. So we will see you for the tomorrow's session. Until then, have a nice day. Bye-bye.